A cycle followed by an engine made of 1 mole of an ideal gas in a cylinder with piston is shown in the figure. Find the heat exchanged by the engine with the surroundings for each section of the cycle. It is given the specific heat of the gas at constant volume is 3 by 2R, and it is also given that the path AB has constant volume, path BC and DA has constant pressure, and path CD is adiabatic. First, in the path CD, as it is adiabatic, there is no heat exchange. So in path CD, delta Q from C to D is 0. Let's analyze path AB. AB is an isochoric process. So and in isochoric process, work done is 0. So work done in going from A to B is 0. Now we know delta U for any process is given NCV delta T, and N in this case is 1 and CV is 3 by 2R. So delta U going from A to B will be equal to 1 into 3 by 2R into delta T. Delta T is the difference between final and initial temperatures of the path. So this is going to be TB minus TA. From ideal gas equation, we can write PA VA is equal to RTA as the number of moles is equal to 1, and at state B, PB VB is equal to RTB. And both the volumes VA and VB are equal since the path is isochoric. So in these two equations, VA is equal to VB. Let's subtract these two equations and find the value of R into TB minus TA. So this is going to become PB minus PA into VA will be equal to R into TB. Substituting back this value of R into TB minus TA, finally we get the change in internal energy delta U in going from A to B as 3 by 2 PV minus PA into VA. From the first law of thermodynamics, delta Q in going from A to B will be sum of change in internal energy and the work done by the system. In this case, the work done is 0 as we have already seen, and the change in internal energy delta U is 3 by 2 times PB minus PA into VA. So finally we get delta Q in going from A to B as 3 by 2 times PB minus PA into VA. So this is the value of heat which is given to the system in going from A to B. Now let's look at part BC of the cycle. So for part BC, it is a constant pressure process. So delta P is 0 and work done delta W in going from B to C would be simply pressure into delta V, which is the pressure in this path is constant and its value is PB, and the change in volume, which is the difference between final and initial volumes, is VC minus VB. So this is the expression for the work done, and let's calculate the change in internal energy. So delta U in going from B to C is NCV delta T, and that can be written as 3 by 2R into delta T, and delta T is TC minus TB. Just like in previous case, by using ideal gas equations, we can write this term as delta U in going from B to C will be equal to 3 by 2 times PCVC minus PBVB. And PC and PB are equal. So this is going to be 3 by 2 times PB into VC minus VB. So from the first law of thermodynamics, delta Q will be equal to the sum of change in internal energies and the work done by the system. We find delta Q as delta Q is equal to 3 by 2 times PB into Vc minus Vb, which is the change in internal energy, plus Pb times Vc minus Vb, which is the work done in the process. So this sum comes out to be 5 by 2 times Pb into Vc minus Vb. So this is the amount of heat which is given to the system in going from B to C. Now we are left out with the path D to A. Even the path D to A is a constant pressure process, and for constant pressure we can directly write delta W in going from D to A will be equal to the pressure in that path into change in volume, which is P D into VA minus VD. VA minus VD because the final state is going to be A and the initial state is D. So the work done comes out to be PD into VA minus VD. And also let's calculate the change in internal energy delta U in going from D to A, which will be 3 by 2 R times TA minus TD. And even in this case, by using ideal gas relations, we can write this as 3 by 2 times PA VA minus PD VD, and PA and PD are equal. So we can write this as 3 by 2 times PD into VA minus VD. So summing the work done in the process and change in internal energy, we get the value of the heat exchange which is happening in this process. So delta Q from D to A becomes the sum of the work done and the change in internal energy, which is going to be PD into VA minus VD plus 3 by 2 times PD into VA minus VD, which is going to be equal to 5 by 2 times PD into VA minus VD. So this is the value of heat exchanged in the path going from D to A.